And welcome to the videos for Math 1500 Calculus 1. So in this video, we're going to be talking about curve sketching, which is going to be kind of a summary and culmination of a lot of different topics that have been discussed in many other videos, both involving the derivatives that you've likely watched more recently, but also some of the other stuff that you might have seen in other videos and even some other pre-calculus stuff that you might not have come across in these videos, but you're probably aware of from previous courses or your own study. So in this one, we are going to be talking about curve sketching. And so let's just remind ourselves, and whenever we're talking about curve sketching, we are talking about drawing the best curve we can that incorporates a lot of different information that we can obtain about a function. So let's review some of those things right now. So the first thing that we usually want to incorporate into our curves is the domain. So when it comes to the domain, we're talking about all the possible values of x that can go into the function, or that we want to go into the function. In theory, we could restrict the domain too. So of course, polynomials, exponentials, domains, all real numbers. When it comes to rationals, dividing by zero, all those similar kind of domain things. The second thing which we can include is going to be intercepts. Now, as we know, there's two types of intercepts that we usually refer to. The easier one is our y-intercept that we get when x is equal to 0. And the x-intercept is when the function, or if it's in terms of y, when y is equal to 0. Now the first one is usually pretty easy. Plug 0 in, see what you get. The second one involves solving an equation equal to 0. Sometimes that can be easy, sometimes it's not so easy. So that one really just depends upon how difficult the question is, but it is pre-calculus solving equation type of thing. The third one is symmetry. Now, there's two types of symmetry that we're talking about whenever we are dealing with a symmetry question. There are other types of symmetries beyond these, but there's two main ones that we tend to focus on, even though you can take it more. There's even symmetry, and there's odd symmetry. So for even symmetry, that's when we are going to be symmetric about the y-axis. In other words, the y value when you have a positive x matches the same y value when you have a negative x. In other words, f of negative x is equal to f of x. The other type of symmetry is odd symmetry, and for that one we would say it's symmetric about the origin. And so when we're talking about symmetric about the origin, that means if we rotated our function 180 degrees about the origin, then we would get, again, the exact same function. Algebraically speaking, that says f of negative x is negative f of x. So in terms of a quick little picture of what this might look like, you could have something like this on this side, and then try and match it up as best you can on the other side. That would be an example of an even symmetry. Whereas an odd symmetry, what you have over here on the right-hand side, you would kind of mirror about both the x and the y and get something on the left. So these are even and odd symmetries, and it's these equations that help us determine when we have that type of symmetry. Now there are other symmetries. You could be symmetric about a different line other than the y-axis. But these are the two main ones that we're referring to when we are discussing symmetry. All right, so that's the third thing that we can incorporate. The fourth thing that we tend to incorporate is our asymptote. So this is where we're actually getting into the calculus. So our asymptotes, and we saw there's two different kinds of asymptotes. We had our vertical. So in other words, we had x is equal to a if the limit as x approaches a plus of f of x was plus or minus infinity, or the limit as x approaches a from the minus sign of f of x is plus or minus infinity. This is usually incorporated somehow with the domain or specifically with continuity. You can only get a vertical asymptote at a if the function is not continuous at a. So this is our vertical asymptote. As for our horizontal asymptote, we get a horizontal asymptote of y is equal to L if the limit as x approaches plus or minus infinity of f of x is equal to L. Now again, you could have two different horizontal asymptotes for the two different ones, the positive infinity, the negative infinity. For things like rational functions, you can only get the one, if any, but for radical functions or exponentials, it's possible to get different answers from the positive infinity and the negative infinity. All right. As for the next thing, this is increase, decrease, and usually when we're dealing with these ones, we can also talk about local extrema. So in this case here, we look at the first derivative. When the first derivative is positive, we get increasing. When the first derivative is negative, we get decreasing. If it changes from increase to decrease, we get a local max. Changing from decrease to increase, we get a local min, as long as it's happening at a critical number. And the last one we usually take into account is all of our second derivative stuff, in other words, concavity and points of inflection. All right. Now again, this is the way it's usually done in 1500. As always, make sure you're following along with your teacher. If they introduce anything extra on top of this, make sure that you're aware of those things as well, whether there are some other types of symmetry maybe, or other things that you talked about in your individual term. All right, and so this would be the second derivative. So this is all the information that we want to take into account when it comes to sketching a graph. Right. So let's take a look at an example and see what we can do. All right, so let's sketch y is equal to 3x squared divided by x squared minus 4, using the fact that we have these two derivatives. Now, again, depending on your term, maybe these derivatives would be given to you in a question like this. Maybe you would be asked to compute them. That can obviously change depending upon the specific test. Obviously, you should be prepared to be able to take the derivative, but that's something that we've definitely talked about, quotient rule and whatnot, in previous videos. All right, so the first four things on our list all come from looking at the function itself. The fifth thing on our list comes from the first derivative, and the sixth bit of information we want to gather coming from the second derivative. In theory, none of what we are going to talk about is new. The new thing is how to piece it all together in the best sketch we can. That being said, most of the work is going through all the different things that we would have seen. So we'll see it in this and a couple more examples. All right, so let's start piecing together some of the stuff. So solution. For our domain is all the possible x values. In this case, we're talking about a function whose denominator can't be 0 because it is rational, and where the denominator is 0, add x is equal to plus or minus 2. So in other words, we can have every real number from negative infinity to negative 2, unioned with all the numbers between 2 and 2, negative 2 and 2, and all the numbers between 2 and infinity. Another way to express this is the set of all real numbers where x is not equal to plus or minus 2. However, it is not acceptable to just write x not equal to plus or minus 2 on its own. That's not a set. A domain is a set of numbers. Just writing the condition on x is not the same thing. All right, so there's our domain. This is coming from the fact that we have a rational function, and therefore our only restriction is the denominator can't be 0. All right, as for the intercepts, as we said, the x-intercepts can be tricky. The y-intercept is usually straightforward. So in this case, let's do the x-intercept first. Actually, let's do the y-intercept first. What I meant to say. So that would say that we're plugging in x equals 0. So that's 3 times 0 squared over 0 squared minus 4. That in fact is equal to 0. As for our x-intercept, that's going to say 0 is equal to 3x squared over x squared minus 4. You can cross multiply, or you can use the idea that a fraction can only be 0 if its numerator is 0 to tell us that 3x squared is equal to 0, and therefore x is equal to 0. In other words, the y-intercept is 0, and the x-intercept is 0. Again, that's coincidental. Obviously, you could get multiple x-intercepts or have y-intercepts that aren't 0, so don't expect that to happen every time. All right, as for symmetry, both even and odd, we can determine by replacing x with negative x in the function. So f of negative x, we're going to plug that in. That's 3 times negative x squared all over negative x squared minus 4. So that's equal to, well, negative x squared is the same thing as x squared. Same thing down at the bottom. And we'll notice that we get the exact same function. In other words, f of negative x matches f of x. So we have an even symmetry. So when we sketch our graph, what we should expect is that everything to the right of the y-axis matches everything to the left, no matter how crazy the function might look. All right, so that's symmetry. For asymptotes, we are just looking at both vertical and horizontal. So for our vertical asymptotes, we're taking a look at where is the function not continuous. So we're not continuous at plus or minus 2. Now that doesn't mean that we necessarily have a vertical asymptote. We can be not continuous for other reasons other than vertical asymptotes. But what it does mean is that if we had any vertical asymptotes, it's at plus or minus 2. In other words, plus and minus 2 are the only possibilities. You can't have any other number being a vertical asymptote. However, how do we verify that we get a vertical asymptote? So we know we get a vertical asymptote if the limit is plus or minus infinity. So we're going to take our limit as x approaches 2 of 3x squared over x squared minus 4. Now again, in a question like this, it's very important that you know what the question is asking. If the question just says, determine the vertical asymptotes, then all we need to know is, does this go to plus or minus infinity? If the question asks you to compute the one-sided limits, then you have a little bit more work to do. You have to do the plus and you have to do the minus. So just be careful about what the question is asking when you're answering this. We're just going to answer, do we have a vertical asymptote? But if the question's asking for more, make sure you're giving more. All right, so this is our 12, aka a non-zero over 0 form, which tells us that this is either plus or minus infinity. Now this doesn't immediately tell us which one. In fact, it might be different on the left and on the right-hand sides. But it is enough information to say x equals 2 is a vertical asymptote, because it is either plus or minus infinity. As for our limit as x approaches negative 2 of the exact same function, we get a similar conclusion. So again, this is the same non-zero over zero form. In fact, because this function is an even function, if you have a vertical asymptote at 2, there has to be another at negative 2. But again, this is plus or minus infinity. So this is enough information to know that our vertical asymptotes are x is equal to 2 and x is equal to negative 2. All right. So again, if the question did ask for one-sided limits, determine whether it's plus or minus infinity, then we would just take the limits from the left and from the right and just see, is it a positive over negative, similar to how you would have seen it in much earlier limit videos. All right, as for horizontal, because we are talking about a rational function, we will get the same answer for positive and negative infinity, which means we can do them both at the same time. For pretty much any other function, we can't do that. You would have to treat them separately. So we have 3x squared divided by x squared minus 4. And so we end up doing what we always do when it comes to a limit at infinity, is we factor or divide by the largest power of x. In this case, it's just as easy to divide because we do have the same powers in the numerator and the denominator, so that we're dividing by x squared, so that's 3 minus 1 over x squared, which is equal to 3. So in other words, our horizontal asymptote, in this case there's just the 1, is y is equal to 3. All right, so we have a horizontal asymptote, we have our vertical asymptotes, we've done all our work when it comes to the pre-derivative information. So first derivative stuff. So this is increase, decrease, local max, local min, even though you could use the second derivative test to find local maxes and mins. The increase, decrease does all the work for us, so there's really no need to go to the second derivative unless you just want to check. The second derivative test usually is helpful in situations where you don't want to find the increase and decrease. All right, so we know y prime was equal to negative 12x divided by x squared minus 4 squared. We need to figure out when is this 0 and when is it undefined. Y prime equals 0 at x is equal to 0. Y prime is undefined at x is equal to plus or minus 2, which turns out to be at the vertical asymptotes. So right here we have that our critical point. Now what are our critical points? Well, critical points or critical numbers are points in the domain where the derivative is 0 or undefined. The particular words there to focus on are in the domain. Well, x equals plus or minus 2 is not in the domain. So those don't count as critical numbers or critical points because they're not actually points on the graph. They're asymptotes. X equals 0 is in the domain, and hence it would be the x coordinate of a critical point. As for the y coordinate, you would have to plug it in. Granted, we already did that when we did the intercepts to know that that's 0, 0. In general, for the y coordinate, you would plug the critical number back into the function. So this tells us some information. First of all, the critical point is the only place where we could have a local minimum or maximum. And second of all, the 0 along with plus or minus 2 are the values we want to put on our number line. So let's go ahead and do that. So y prime and y, 0 because it's a critical number, plus and minus 2 because they are points where the derivative is undefined. And then you can hit this with whatever method you might have learned in order to figure out when it's plus, the derivative is positive or negative. We'll do the one that we discussed in our video from increase and decrease, but if you have another method, as long as, and you may want to verify with your instructor, as long as it is a method that works all the time, that's probably fine. But if you are doing a method that's a little bit different than this, you may want to check with your instructor to make sure it's okay and that it always works. All right, so we're going to plug numbers into our function, or into our derivative function. So for example, if we want something bigger than 2, so that's going to be y prime at 3. So that's 12 times 3 over 3 squared. That's 9 minus 2 squared, or 9 minus 4 squared. So we could compute this. This is negative 36 over 25. That being said, the moment we know that this thing is negative, because we have a negative in the numerator, and because we're squaring it, definitely have a positive in the denominator, we know that this is negative. In other words, the derivative is negative, so our function is decreasing. Y prime of 1, that's negative 12 times 1 over 1 minus 4 squared. Again, that's a negative divided by a positive, so that's still negative. So it's negative, and we're decreasing. Something between negative 2 and 0, for example, negative 1. So we're just testing values on each piece. That's 1 minus 4, again, squared. The numerator is now positive. The denominator is also positive, so our derivative is positive. Since the derivative is positive, our function is increasing. And lastly, something less than negative 2, y prime of negative 3, for example, negative 12 times negative 3, all divided by 9 minus 4 squared. Again, that's a positive divided by a positive, hence it's going to be positive. So we can test values on each of these 4 subintervals, and we can get our increase and decrease information. We can also notice at 0, it changes from increasing to decreasing, so 0 is a local maximum, and there are no other critical numbers, and hence there's no local minimums. And so we're increasing on the interval from negative infinity to negative 2, and negative 2 to 0. Technically, it's wrong to put a union of intervals. We don't define increasing on a union. It makes even more sense when we actually sketch the picture. We're decreasing on 0 to 2 and 2 to infinity. One thing to note about this, before we get to the other 2 pieces using the first derivative, is that if we had said negative infinity to 0, that's wrong. It's wrong to say negative infinity to 0 because the function is not defined at negative 2. And in fact, when we do sketch the picture, we're going to see something that looks like this, which we wouldn't say that this is an increasing function because over here, a bigger x value gives you a smaller y value. It doesn't make a lot of sense. So that's why we don't put a union, and it's also why we don't combine these intervals together. That being said, if we were actually defined at negative 2, then you could. That being said, it's still not wrong to leave it as is. So we get a local max at 0, 0, and no local min. So this is all the first derivative information that we can have. And we'll do something very similar with the second derivative to get the concavity information. So lastly, we have our concavity. So y double prime is equal to 72x squared plus 96, all divided by x squared minus 4 cubed. This is never 0. This is never 0 because our numerator is always larger than 96. If you don't see that right away, that's fine. We can actually try and solve it. But if we had 72x squared plus 96, that would tell us that 72x squared is equal to negative 96. If you don't see it there, you can get x squared is equal to negative 4 over 3 by dividing by 72, and we get x squared is equal to something negative. That can't happen, but let's say we even didn't notice that, and you actually solve for x, you get a negative under your square root. And that's impossible. So this is never 0. It is undefined. At plus or minus 2. Again, not a surprise. The first derivative wasn't defined, so neither will the second. All right, so this means on our number line, we're going to include plus or minus 2, because those are the places where the derivative is in fact 0. Or sorry, is undefined. It's not 0. So, second derivative, we'll put in the negative 2 and the positive 2, and do the same thing of testing. So, y double prime of 3, that's going to be 72 times 3 squared plus 96, all divided by 9 minus 4 cubed. So again, we could compute this. This is 74 times 9 plus 96, whatever that is. But we know that numerator is positive. Denominator is 5 cubed. We also know that numerator is positive, and hence we end up, or the denominator is positive, and hence we get that the second derivative is positive. Hence we're concave up. Something between negative 2 and 2, for example, 0. That's going to be 72 times 0 plus 96, all divided by negative 4 cubed. That's a positive divided by a negative, so that's negative. In other words, we're negative. Again, you'll notice here, that kind of verifies that we end up getting a local maximum like we saw before. And something less than negative 2, for example, negative 3, that's 72 times 9 plus 96, all divided by 9 minus 4 cubed, which again is positive. So we're concave up, excluding negative 2 to 2 when we're concave down. We also know for points of inflection are points where we change concavity. And this function doesn't change concavity at points because negative 2 and 2 gave us asymptotes. All right, so putting everything together, we're concave up on the intervals from negative infinity to negative 2 and 2 to infinity. We're concave down on negative 2 to 2, and we have no points of inflection. Again, reason for that is that there's no point where the concavity changes. So this is how we can derive all the information for which we're going to use to sketch the graph. So let's put all that information on a picture. All right, so we're putting all the information on here, the domain, everything except plus or minus 1 for intercepts, we got 0, 0. That's an important point. Also happened to be a local maximum, so we can put a little maximum here. I strongly recommend doing this stuff with a pencil. There's a lot of little erasing that you're probably going to want to do. Next step is symmetry. What happens over here on the right is going to match what happens over here on the left. As for asymptotes, we had y equals 3. And we had x is equal to negative 2. And positive 2. All right, so these are all the important points, and we'll notice that the asymptotes and the local maxes and the points of inflection, although in this case we didn't get any, separates our graph into 4 pieces. So we're going to analyze the increase, decrease, concave up and concave down on each of these 4 pieces. The reason we have 4 is because of how the local maximums, the local minimums, the points of inflection, the asymptotes separate our function. Sometimes you might only have 1, sometimes you might have 10. It depends on how many of these key features we have, which is why it's important to label them and get them on our picture right at the beginning. All right, so we're going to start off between negative infinity and negative 2. On that region, we know we're concave up, and we know that we're increasing. So we're increasing and concave up. So that means that we have something like this. Because we're increasing, that means we go to the top of the vertical asymptote. We can't be increasing and go down to this bottom. Also, because we're increasing this whole time, we have to start above this horizontal asymptote. Because we have to start really close and get really, really close to it. That doesn't mean you can't cross the horizontal asymptote. You certainly can. But you're not going to start like this. Then you'd have to go up. That's okay, but that would mean we have a local minimum. Changes from decrease to increase. So if we're starting increasing, we start by going above the horizontal asymptote. If we start by decreasing, we go below. Or you can think about what the concavity would look like on each side. All right. In this second piece, negative 2 to 0, we know where you're going to be concave down, but we also know that we were still increasing on that piece. So we're increasing and concave down. So that means we have this piece. Since we're increasing, we have to start down here at the bottom. You can't start at the top and be increasing and still manage to get to 0, 0. And so we're increasing to here, and then we stay concave down from 0 to 2, but we change to decreasing. So now we're decreasing. So on each piece, we're just doing increase, decrease, concave up, concave down. And we're piecing everything together. To the right of 2, from 2 to infinity, we're still decreasing based on our information, and we're back to being concave up. So we're concave up but decreasing, and we have to go to that horizontal asymptote. So there's our picture. So we have our 0, 0, that's our local max. We have our asymptotes, both horizontal and vertical. So that's how we can sketch one of our graphs. All right, so let's take a look at another rational example where we're going to piece together a lot of the same information. So we're going to sketch another rational function, again given a couple of the derivatives, the first and the second derivative. All right, so again, start off the same way. Again, it's rational. which means that our domain, we have to be concerned about when the denominator is 0. Before we do that, because we'll see it in a few different places, x squared plus 3 is not equal to 0 for any x. That would mean x is equal to plus or minus the square root of negative 3. We're actually going to see that in a few places, which means it's good to get that out of the way right at the beginning. So first of all, our domain is all real numbers. So again, either negative infinity to infinity or the real number sign. Again, it is rational, but the denominator is never 0. In fact, this tells us more than that. Because it is a rational function with domain all real numbers, we also know it's continuous everywhere, which means there's no vertical asymptote, which we'll get to when we get to the asymptotes. Right, our y-intercept is 0 squared over 0 squared plus 3. That's equal to 0. Our x-intercept, that would say x squared over x squared plus 3 is equal to 0, which tells us that x is 0. So again, the x and y intercepts are both 0. It's a coincidence, but we do get that. Our symmetry, f of negative x is equal to negative x squared over negative x squared plus 3. Once again, we're squaring the negative term, so that's x squared over x squared plus 3, which is equal to f of x, which means we're even. Now, if we go back to the previous example, we were even there as well, and you can kind of see what happened over here is matching what happened over here. So we should see something similar happening in this second example. For asymptotes, so we have no vertical asymptotes since f is always continuous. If you're continuous, then the limit has to exist everywhere, and hence can't go off to plus or minus infinity at a specific number. That doesn't mean we don't get a horizontal. For horizontal asymptote, we take our limit as x approaches plus or minus infinity of x squared over x squared plus 3. Again, that's our limit as x approaches plus or minus infinity, dividing top and bottom by x squared. Again, we can do that more easily here because it is the same power. If it was different powers, we probably want to do some factoring. And so y equals 1 is, in this case, once again, the only horizontal asymptote. So there's no vertical, but there is one horizontal. All right, so that's all of our pre-derivative information. As for the derivative information, let's take a look at our first derivative. That was equal to 6x over x squared plus 3 squared. All right, so again, this is going to be undefined. Absolutely never. So this is never undefined. Again, the reason it's never undefined is for something we wrote down earlier. That denominator is never 0. X squared plus 3 is never 0, so the denominator is never 0. As for when it's equal to 0, that would mean 6x is equal to 0, which tells us x is equal to 0 divided by 6, which is 0. So this is our critical number. As for our critical point, well, x is 0, so our x-coordinate is 0. Our y-coordinate, you'd plug 0 into the function. So plug 0 back into this original function. However, we already did that with our intercepts. and saw that it was equal to 0 as well. So our only critical point here is 0, 0, which means we can only have one local minimum or local maximum at all. We may not even get one, but we can get at most one. All right, so number line, the only number to put on our number line is 0 because it's the only place where the derivative is 0 or undefined. So we'll just test something on both sides of 0. So something bigger than 0, for example 1, that's 6 times 1 over 1 plus 3 squared. Again, that's going to be 6 over 16, but all we care about is that it's positive. Hence the function's increasing. Take something less than 0, for example negative 1, that's 6 times negative 1 over 1 plus 3 squared. That's negative 6 over 16, so that's less than 0. And hence we're decreasing until 0 and increasing after 0. So that gives us our increase and our decrease. Second thing to notice is that we are decreasing and then increasing, so 0 is a local minimum as well. So we're increase on our interval, in this case just the one interval, from 0 to infinity, and we decrease on our interval from negative infinity to 0. We get a local max, local min at 0, 0, and no local max. There's all of our first derivative information, which obviously we'll use to sketch the graph. All right. As for the second derivative information, that's going to be 18 minus 18x squared all over our denominator cubed. Again, as before, this is always defined. The denominator still is not equal to 0. As for when it's equal to 0, then it gets a little bit more interesting. So that's going to tell us that 18 minus 18x squared is equal to 0. You could factor this, or you could see that that happens when x squared is equal to 1, dividing by 18, and hence x is equal to plus or minus 1. All right, so we get that the derivative is 0 at plus or minus 1, and hence these are our possible points of inflection, where the second derivative could change sign. All right, so testing something on each of these three pieces, that says the second derivative of 2 is going to be 18 minus 18 times 4, all divided by 4 plus 3 cubed. So that's negative 54 divided by 343. But again, it's a negative divided by a positive. That's all that really matters. And so we get that we're concave down. Testing something between 0 and 2, so that's 18 minus 0 over 3 cubed. That's positive. Hence our second derivative is positive. We're concave up. Once again, verifying that we're a minimum here at 0. And testing something less than negative 1, for example, negative 2. And we get 4 plus 3 cubed again. So that's 18 minus 72, which is negative, divided by a positive. All right, so this gives us all of our concavity information, and that we have points of inflection at plus or minus 1. Now, since we do have points of inflection, we will want to compute the y's. So this is y of f of 1, so that's 1 over 1 plus 3, which is a quarter, and either using that it's even, and hence f of 1 equals f of negative 1, or computing directly, we can also get a quarter for negative 1. And so we're concave up on our interval from -2 or -1 to 1. We're concave down on our intervals from -infinity to -1 and 1 to infinity. And we have points of inflection of 1 a quarter and -1 a quarter. So this is all of our second derivative information. All right, so now we can piece everything together and draw the best picture we possibly can. So here's our grid. We have a horizontal asymptote of 1. We have no vertical asymptotes. Our domain is all real numbers. We do have 0, 0, which also happens to be a minimum, a local minimum. We have 2 points of inflection of -1 and +1, 4. Or quarter, not 4. And that splits, again, our function into 1, 2, 3, 4 regions for which we want to analyze the concave up and concave down. So from -infinity to -1, we're going to be concave down and decreasing. That's concave down and decreasing. From -1 to 0, we're going to be concave up, but still decreasing. We can verify here, clean it up a little bit, aka use a pencil. We can get that our function is concave down and then changing to concave up because we had a point of inflection. From 0 to 1, we're still concave up, but now we're increasing. Again, 0, 0 is our local minimum. So that gives us this third piece. And from 1 to infinity, we are increasing in concave down and have to go towards this horizontal asymptote. So except for the fact that we created this little bump here that wasn't particularly smooth, we get something that's also even. What's happening on the right side matches what happens on the left. So here we have another graph of a rational function. So in our next video, we'll actually do a couple more examples of curve sketching, but talking about non-rational functions and see some of the changes that happen there.